Welcome to the final video demo of ECE Capstone Project Spring 2023. We are Team B3 Mobile Steering Wheel. Our project is a wireless gaming controller that allows users to play racing games with a steering wheel-like peripheral. By tilting our controller, the user is simulating the action of turning a steering wheel in a real car. Combined with our analog gas and brake inputs, programmable push buttons, and an LCD dashboard, our product offers a highly immersive experience without breaking the bank. After a whole semester of hard work, we cannot wait to showcase our project. There currently exist steering wheel controllers for racing games on the market, but none of them quite suit our needs. They are quite expensive, and most of them take up a lot of space to set up. As college students, we don't have a lot of money to invest in an expensive piece of gaming peripheral, nor do we have large apartments where we can set up such a big device. Most of us live in dorms or some sort of apartments shared with roommates. We need a portable and cheap steering wheel controller which still offers some level of immersion. I'm Xiao. I'm responsible for the hardware part of our project. Racing games, unlike most other video games, benefit a great amount from appropriate peripherals. Take gas and brake input for example. If they are controlled using a keyboard, then you only get full gas or no gas, full braking or no braking. This is not how cars are supposed to be controlled. When switched to analog inputs, you have fine control over gas and braking. This is why our controller has two potentiometers for gas and brake control. They are connected to an analog to digital converter to talk to the brain, a Raspberry Pi. Steering is a similar story, and we use an IMU, inertial measurement unit, to sense the changes in posture, and more specifically the changes in the tilt angle of our controller. To further add immersion, we designed an LCD screen to show the dashboard of a car, and 12 programmable buttons to be mapped to any function in games. Our controller also has an ergonomic enclosure for the comfort of our users. Power delivery is handled by an intelligent power management system, and battery life is expected to be around 4 hours. The controller communicates wirelessly with PCs over Bluetooth 5.0. A short clip of our controller in action is at the end of this video.
My name is Chao Shen, and I am the team member responsible for the gyroscope tuning part of our project. The critical section aims to determine the orientation of our steering wheel based on sensor readings from the IMU installed on our device. The IMU has three components: a gyroscope, an accelerometer, and a magnetometer. The gyroscope provides us with angular rate data, which we can integrate to determine the orientation amount. However, this approach is subject to integration errors and gyroscope drifts. The accelerometer and magnetometer use gravity and the magnetic field to help us determine the steering wheel's orientation, but they have higher noise levels and are easily affected by shaking. We use the metric filter to generate the orientation by combining data from all three sensors. This filter converts the readings to quaternions and combines integrated gyroscope data with gradient descent result based on accelerometer and magnetometer readings in quaternions. We choose to have a high learning rate for the gradient descent to respond quickly to rapid rotations, though this may result in overshooting and increased noise levels. Next, we transform the quaternion back to order angles in ZY-X sequence to avoid the gimbal lock problem in our use case scenarios. As the XYZ sequence faces issue and loses its freedom when the pitch approaches 90 degrees. We then apply the common filter to filter out noise from the measurements and metric filter processing. The filter makes predictions based on the uncertainty for measurements and its current state, which is the orientation estimation we currently have. Finally, we map the filtered orientation estimation in degrees to the analog input of joysticks. We apply that zone on the mapped joystick inputs around 0 and 1, as we want to make sure users can reach both ends of the inputs easily.
Hi, my name is Yuxuan. In this project, I'm responsible for writing the software program and making sure that the two devices are connected through Bluetooth. Let me briefly talk about how the data is transmitted through the two devices within our software programs. When a user presses a button, the program running on Raspberry Pi will read the raw button and sensor information and runs the gyroscope tuning algorithm. The algorithm will try to reduce the noise of the gyroscope and filter out the noise within it. After running the gyroscope tuning algorithm, it will then send the data to the data transmitter program that is running on the Raspberry Pi. The data transmitter program is connected to Windows PC through Python socket using RFCOMM protocol, which is a Bluetooth communication protocol. When the Windows PC receives the raw button information from the Raspberry Pi, it will try to translate the raw button information into a format that the game running on the PC can understand. In this case, we're using an Xbox emulator library, which allows us to map our raw button inputs into the Xbox inputs so that we can call the library methods to update the game movement on the screen. On the other hand, we are also trying to display the real-time car information that is running on the PC on our dashboard, which is connected to the Raspberry Pi. To achieve this, on Windows PC, we are running a program that continuously collects the data from the beamng.drive game through the out-gauge protocol provided by the game. In another program running on Windows PC, it is continuously reading the real-time car data from the file and then transmit the car information back to Raspberry Pi through the same Python socket. On Raspberry Pi, there is a Node.js backend running as a middleman, which allows the Python program to post the real-time car information once it receives the information from Windows PC. And the Node.js backend also allows the dashboard, which is implemented in HTML, CSS, and JavaScript, to continuously fetch the information from the Node.js backend. In this case, since the dashboard can continuously fetch the real-time car information, the dashboard can be continuously updated.